So good morning, everybody, and welcome. My name's Cathy Constable. I'm a professor here at Scripps and the Earth Section head, and I just want to kick us off with a few opening remarks. We're here today to celebrate Margaret Leinen's career and also to express our appreciation for all that she's done in her role as director of Scripps since she joined us in 2013. She's not just our director, she's also a Vice Chancellor for Marine Sciences, Dean of the School of Marine Sciences. So what that tells you is she has major administrative and educational responsibilities as well, just in case you didn't know. And of course, I think everybody in this room knows that she's an award-winning oceanographer. She's a distinguished national and international leader in ocean science. And I'm not going to read out all of her awards because that would embarrass her, because there are so many. And she has carried out research in paleoceanography, paleoclimatology, worked on ocean sediments, and she's worked on climate in the past, present, and future, as we're going to hear about today. She served at the National Science Foundation as an assistant director for 7 years, so she's got a huge footprint in what I like to call science administration and diplomacy. And she served as a US science envoy and as president of the American Geophysical Union, among many, many other things. So when we put together the program for today, we had to make some decisions. And we chose to go with some science talks about marine sediment, an overview of how oceanography has evolved in the world since over the past decades, and some work on carbon dioxide removal. And then we're going to hear from some people who have been involved in science management in the AGU, in NSF, and also from a group of our students who are going to tell us what it's like to live and work and grow up in the US science establishment. So that's the general idea. But a couple of things before we start. First of all, I'd like to recognize and thank a very special couple who are in the audience here, Doctors Ellen Lehman and Charlie Kennel, who have provided an incredible amount of funding to Scripps Institution of Oceanography and given us an opportunity for a lasting impact through the Charles F. Kennel Endowed Director Fund. And going forward with this great gift, the director of Scripps Institution of Oceanography will be named the Charles F. Kennel Director of Scripps Institution of Oceanography. So. Then I've got a couple of housekeeping items. Many of you know the restrooms are out in the back corner and around the corner. Those of you who are speaking, Kyla is the tyrant timekeeper, and she has little signs that she's going to hold up that say 2 minutes, 1 minute, 30 seconds to keep us moving forward so that we get through the program over the course of the day. And I think that's all that I had to say. Now we can turn to our program, which will be kicked off with a keynote by Rick Spinrad. And until January, he served as the administrator for the National Oceanic and Atmospheric Administration and Under-Secretary of Commerce for Oceans and Atmosphere. And he's well known. He has a career that spans government appointments at ONR and NOAA and all those places, and we're looking forward to hearing from him. And now I just have to figure out how to get his talk up.
Better you than me.
Yeah, that's what I'm thinking too. What happens if I do that? Ah, this looks like it. Okay. Okay, it's all yours, Rick.
Thank you, Kathy. Well, I could spend the next 40 minutes or so just saying what an honor it is to be here, what a special treat, and what a real personal honor it is. I've known Margaret, well, let's just say decades, okay? Let's agree, let's just say it's decades, and it's several decades. We've worked together in a variety of different capacities. But I also want to say what a treat it is to be here at Scripps, and I was realizing that for a large portion of my career, I was a program manager at the Office of Naval Research, and some of you in the crowd will remember when we did regular site visits here. And I was remembering 35 years ago, I had a career-changing activity. I came here for the site visit. It was always the first week in June. And Walter Monk was giving us a lecture on the Herbert Island experiment. And those of you who know Walter's amazing ability to take these very complex scientific issues and translate them into these exquisite concepts for science, the Herbert Island experiment was that. The short part of this story, which ties me into what I want to talk about here today, is that basically the Herbert Island experiment involved insonification of the ocean. And there was word that got out, incorrect, I guess you'd say fake news, about the level of insonification and the potential impact it might have on marine mammals. And the Marine Mammal Commission at the time started this whole flurry of activity, which basically meant that Walter had to go to commission hearings in Honolulu and San Diego and justify with the work that was going to be done, and that it was going to be done in a well-controlled manner, and that marine mammals would not be hurt by this. And I remember Walter telling me about how frustrated he was, but as only Walter could do, he said he would get on a plane to fly from San Diego to Honolulu, sit down next to someone, they'd say, "What do you do?" And he would share what they're doing. They'd say, "Oh, you're the one who wants to kill all the whales." And Walter, he would say, by the time we landed in Honolulu or flying back to San Diego, he had convinced that person that this was a wonderful idea. And he said to me, "So the way I figure it, Rick, I only need 1 million more flights between San Diego and Honolulu." And that's at the heart of what I want to talk about here today. This is the somewhat dry title that I put up. But really what I want to talk about is how oceanography saved the planet. And more specifically, what I want to do is talk about how the world that we live in right now is a better place because of ocean sciences. And I'll do a little bit of a retrospective. And because I have the honor and the authority as a keynoter here, I also want to talk about how Margaret Leinen made oceanography a better science, and those two go hand in glove. So let's start by talking about, well, what is it that oceanography has done? And I'm going to be a little bit bold, and this is where that anecdote about Walter comes in, because it's up to us, it's up to the ocean sciences community to make clear that, for example, it was oceanography that helped end the Cold War. It's oceanography and ocean science and environmental science that heals us, that keeps us fed, that improves our quality of life, that tells us about the origins of life, that unlocks sources of energy, is key to forecasting weather, and actually saves us time and money. I'm going to talk a lot about the what and the why in my talk, and looking at the agenda, we have an exquisite set of discussions that will talk about the what and the why, but also about the how. I'm going to spend less time talking about the how, because I think the most important thing we need to do is talk about impact. We need to talk about what we are doing and how it relates to the person in downtown San Diego, the person in Dubuque, the person in Madras, the person in Hanoi. It affects the global population. And it's not just me saying that. You see this in the press every day. I used to give a course at the Naval Academy where I would bring in the Washington Post of that day, and I would peel it off and pass out the pages to the midshipmen, and I'd say, find something that's tied to ocean science in here. And I did this for years, and I never had on an occasion where we could not find at least a half a dozen items in the daily newspaper that related to ocean science in one way or another. And so what I'd like to do in the next several minutes is walk through some of these examples. This is the retrospective part of the talk. This is where we're going to look at just what the impacts have been. And I thought I would start with one that is very near and dear to this particular institution. Scripps has had a wonderful relationship with the United States Navy for many years. But I took a little liberty. Cathy, in introducing, said we're going to look back a few decades. I thought I'd just start a few centuries and point out that, in fact, when you look at national security, the Chinese explorer Zheng He was actually one of the first to demonstrate with his, and this was in 1405, that he conducted explorations with his new vessels called the Bao Chuan, which was an exquisite new design for a vessel. But he also recognized that mapping and charting in what we now call geodesy were critical to his operations, operations which were inherently military, but were couched in a sort of trade mission, a cover, if you will. So shipbuilding, hydrographic surveys and measurements, mapping and charting were part of this start in the treatment of ocean sciences as it relates to national security. Jump forward a few centuries and you have the Pathfinder of the Seas, Lieutenant Matthew Fontaine Maury, who was commissioned in the United States Navy. Then he had his own sort of a make the South great again moment, I guess, and he converted over to the Confederacy. But before the Civil War broke out, he realized that it's critical for national security purposes that we actually bring all the nations together and see, what are you collecting, what kind of data have you got? And so he initiated the Brussels Conference in 1853 to bring the nations of the world together. And based on that, he published this volume, The Physical Geography of the Sea. Take a look at it if you haven't looked at it yet, especially the students in the audience. It's really a phenomenal collection, given that it's 170 years old, of what the value of this comprehensive global observing network needs to be. Jumping ahead another century, of course, you cannot talk about national security without talking about Walter Munk and Harald Sverdrup. And I don't need to lecture this audience on the value of the work that they and the people that were working for and with them did for things like improved wave forecasting to support the D-Day invasion. But I also want to call out Mary Sears. Mary Sears, who was a woman oceanographer identified by Roger Revelle to be enlisted into the United States Navy and start up what is basically our modern hydrographic capability in the US Navy. And in fact, she was critical in defining the way forward in understanding coastal dynamics and helped in any number of invasions, including Okinawa and other Pacific theater operations, and so much so that she was recognized with a commendation by Admiral Nimitz. She set the course for Navy METOC, meteorology and oceanography. And then you get into the modern era, and like I said in that earlier slide, oceanography did help win and end the Cold War, and one of the critical players in there was Marie Tharp. Now, many of you may think I should say Bruce Hazen and Marie Tharp, but I think history has shown us the role that Marie Tharp played in terms of taking volumes and volumes of data and translating that to literally a picture of the globe, a picture of what the bottom of the ocean looks like. Information and data, and she did this at Lamont, that turned out to be critical in terms of how the United States submarine forces operated. The other piece in this picture in the Cold War is a personal favorite of mine. It involves the guy in the upper right, Paul Scully Power, who is Australian, but he's a physical oceanographer who worked at the Naval Undersea Warfare Center in Connecticut. And he was the first ocean scientist who actually went up in space. He went up in the shuttle and he took this photograph of the North Atlantic. And it was one of the first real clear observations of the warm core rings, the eddies, this extraordinarily complicated pattern just of the surface of the North Atlantic. At the time, there was a fellow named James D. Watkins. Jim Watkins was the chief of naval operations. He was a submariner. And since Scully Power had been a Navy employee, he was required to go debrief the chief of naval operations. He went and debriefed Watkins. Watkins, being a submariner, said, "Is that stuff going to screw up my acoustics, my ability to detect submarines or to hide?" And sure enough, the answer is, yeah, we think so. And the consequence of that is that Navy developed under Watkins' leadership, although John Lehman, who was Secretary of the Navy, claims credit for it at the time, a whole new ocean policy. Now, if you look, there's a paper from July 1984 by a fellow named Lieutenant Commander James Stavridis. Some of you may know Stavridis went on to become the Supreme commander, a NATO commander in Europe. This was fundamentally a pivot for the United States Navy, saying, maybe we better get a better understanding of the ocean. And so a whole bunch of policy changes were put in place. Curricula at the Naval Postgraduate School, new ships were built specifically to purpose to go out and study the ocean. Whole new classes, line officers who were called 1800s, METOC officers were created. And the idea here was that maybe we'll get a better understanding of the nature of acoustics. Now, I'm not going to walk through Acoustics 101 to this audience. I suspect all of you understand what's being shown here. The basic idea, though, is that, hey, we can take advantage of this concept of a sound channel. Oh, by the way, this was exactly what Walter was talking about in the Heard Island experiment. But not only that, we get a little smarter, and we're going to be able to figure out where to hide our submarines in the shadow zone shown in this particular picture. The outcome of this, the outcome of that intensive effort to understand ocean sciences at an extraordinary level of detail in 4 dimensions, was the establishment of the Integrated Undersea Surveillance System. A system which included static observations through the Sound Surveillance System, or SOSUS, arrays up and down the US east and west coast, as shown in the upper right, as well as CERTAS, which was the towed arrays, the systems that could actually go throughout the ocean looking for the submarines of the evil empire. And don't forget the P-3s that were flying as well. The insignia in the lower right indicate that anti-submarine warfare came of age at this point because we learned how to make these observations. And young officers like Ensign John Orcutt, for example, were introduced into this field, this science that was supporting our national security objectives. And I'm here to tell you that because of systems like that, in 1989, George Bush and Gorbachev were able to declare that the Cold War is over. And I would love in a Q&A session to defend the role that ocean sciences played in ending the Cold War. But it not only saved us from a Cold War, I'm going to shift gears and say it saves us from disease. And I think about the role ocean sciences has played in our health, and I am so honored and delighted to be here in the audience with Dr. Rita Caldwell, who I know will speak with us later today and has been a pioneer in demonstrating the role ocean sciences plays in addressing disease and public health, as have people like Bill Fennekel and Shirley Pomponi. We could spend the rest of the time talking about this, but this montage is showing you that things like toxins from cone snails are going to address neuropathy. On the right, upper right, you see Caribbean sponges that have now been used by Pfizer to develop an FDA-approved drug treatment for leukemia and lymphoma. Similarly, discodermalides from sponges are being used to treat breast cancer. Steroids from corals are being used to address asthma. And you could say, well, why is this an ocean sciences issue? Well, first of all, where are these organisms? We need an exploratory capability. It's not necessarily easy to go find some of these things. Second of all, do we understand the relationship between the environment and these ecosystems, these organisms? And third of all, what about the ethical issues associated with bioextraction? So these are incredibly complicated issues in which ocean sciences is firmly embedded. There's also aspects, obviously, of oceanography that are relevant to our food security. And I would argue health is partly defined by nutrition and food. And you think about what's happened in the world the last several years. I think everybody knows that oceans are this extraordinary source of protein for the world. But while I served as NOAA administrator, one of the urgent issues across my desk was the complete decimation of the salmon populations in the Yukon and Kuskokwim rivers. They weren't there. No salmon. And I found myself in the middle of a debate between the native tribes and the geneticists who were working for NOAA. And the debate was, well, obviously there's no salmon in the Yukon and Kuskokwim because the bycatch from the pollock fishery in the open ocean is decimating the populations of salmon. And the geneticists saying, no, the bycatch is all Asian salmon. it's not salmon from those rivers. So you talk about a complicated scientific problem that addresses our critical need for nutrition. The fisheries is obviously that. And it's also tied, you know, the food and food security and nutrition aspect is tied to aquaculture as well. And there have been some wonderful developments. This happens to be something, dulse, that was raised by several different communities. Oregon State University did a lot of work on this. Turns out dulse is basically seaweed that tastes like bacon. Doesn't get any better than that, right? So where do you put in aquaculture facilities? How do you put them in? What observations do you need to support those activities? Are the concerns about ecosystem impacts real? What about the disease vectors associated? So all of these issues, and oh, by the way, don't forget, in the United States alone, the fishing industry is a $320 billion industry that employs over 2 million people. So we better get it right. But wait, there's more. In terms of quality of life, you know, everything from the ice cream that you eat and the yogurt that you eat that depends on alginate derived from macroalgae to, this is one of my favorite stories, the microbial breakdown of whale bones in the deep ocean has yielded understanding about cold water enzymes. Obviously, it's just a couple of degrees down where those whales are decomposing. And the industry that makes laundry detergent has been looking for cold water enzymes for years. And now we're looking at these microbial populations and the enzymes they create. It might help save our use of energy for hot water, for cleaning our clothes. There's so many other things. There's a sea-whip-derived chemical that turns out to be an extraordinary analgesic and anti-inflammatory. And then there are also marine microbial mats that have an enzyme that has now been found to be unique and critical to the production of biofuels. So there's a big debate, and I'll talk a little bit more about it in a few minutes, about deep sea mining. And I would just remind you that mining is not necessarily just grabbing cobalt on the ocean floor. There's mining activity that can happen associated with biomaterials as well. I'm going to shift gears again. This is also another safety issue. This is one of my favorite stories because this came to light for me when I was the head of research at NOAA. Obviously, NOAA is very active in hurricane forecasting. Let's see if we can get this video to play. This is the geostationary satellite image of Hurricane Katrina in 2005. And what I want you to focus on here, this is the full evolution of the hurricane. It'll start southeast of Florida as a tropical depression, turn into a tropical storm. And then you'll see it cross into the Gulf, and it will intensify. And what I want to give you a heads up on, as you watch it form here, there right about where the pointer is, it's a tropical depression now it's starting to get some rotational definition, so it's turning into a tropical storm, crosses over Florida. As it crosses into the Gulf, watch the eye form. Now remember, this hurricane turned into a Cat 5 hurricane over the Gulf. You can tell it's a Cat 5 in this particular video because the eye of the hurricane and the eye wall are crisper than you will probably ever see. Let me move that out of the way. Watch the eye wall, watch the eye wall, watch the eye wall, and bam. That's Cat 5. Degraded, it turned into a Cat 3, ultimately on landfall. Okay, so that's the setting. Now let's see if I can get this to move on. And the common thinking at that point was that this is what happens. So you see, first of all, the track of the hurricane, the dots. The color of the dot tells you the intensity, basically scaled to the Saffir-Simpson scale, with blue being about Cat 1, light blue, and bright red being Cat 5. And then the underlayment there is sea surface temperature. And the thinking all along was, well, just look at sea surface temperature, and that'll tell you where you're going to get the energy for the intensification of the hurricane. Just from your eyeball look on that, it does not correlate well. There's no reason to believe that it should intensify there in the middle of the Gulf. Now, this is where I remember, as a card-carrying oceanographer, going to my friends saying, that's the trouble with you meteorologists. You only think of the ocean as a two-dimensional system. Now look at sea surface height anomaly. And you see something different is going on there. And anybody worth their salt knows that the sea surface height anomaly, of course, is a manifestation of the total heat content, right? So the idea here was you can't just take a satellite or fly over and take a surface radiometric measurement and say, okay, we can do a much better job of predicting intensification. You have got to have the full four-dimensional characterization of the physics of the ocean. The only way you're going to do that is by measuring the full ocean. And this is where I've got to do another tip of the hat. The spray glider on the left, the Argo buoy on the right, without people like Ross Davis and Dan Rudnick and Dean Remick and Sarah Perky and many others, and obviously Doug Webb, we wouldn't have these technologies. And I've had the honor of seeing where they're put together, where they're built. Because what these devices do for us is they allow us now to characterize, and what you're seeing in the upper left is the tracks, the glider tracks, and I apologize, I don't remember what year that was, but it's 1 year's worth of glider tracks as deployed by NOAA with cooperation from people like those I've just mentioned. And then on the lower right, you see what is basically that sea surface height anomaly chart, but now it's characterized in terms of total cycle heat potential, kilojoules per centimeter squared. And now it's crystal clear. Our ability to improve both the track and intensity of hurricanes. There have been a lot of things that have been done. We've improved our capability to launch flights and to launch drones, but I firmly believe that it's the oceanographic contribution which has resulted in improvements like this. And bear in mind, that improvement in the track, the actual track as forecast for Katrina in 2005, the simulated track as to what it would have looked like in 2015 based on the new observations. What I don't have on here is the 2025 track, what it would look like today. But what I can share with you is that we know this. We know that the track errors now for the 24, 48, 72, 96, and 120-hour forecasts have improved to the point, and oh, by the way, while I'm talking track, similarly on intensity, but not quite as much. But the general rule of thumb is that every 10 years we improve the hurricane forecast by 24 hours. The 72-hour forecast today is as good as the 48-hour forecast was 10 years ago. And that is largely because of the oceanographic capability and observations. Let me move on. Let's talk about saving dollars, saving time. 99% of the cargo by volume shipped into and out of this country, even with tariffs, is by sea. The other interesting rule of thumb is that a commercial shipper will tell you roughly it's $1 million a foot of clearance. As you load that ship, obviously, if you're loading it with Lamborghinis, it's going to be different than if you're loading it with wheat, but about $1 million a foot. And this is where one of the most exciting aspects of what we're doing in oceanography starts to come out. It's what I call the new blue economy. So much of what I've been talking about in the last several slides has been extractive in nature. Fish, biochemicals, didn't talk a lot about mining, oil and gas is extractive. The currency of the realm for the new blue economy is data. It's the data that we are extracting from the ocean. So think about this. Think about the shipping challenges in the port of Portland. So Portland, Vancouver's the main port across the river from Portland, is mostly a grain shipping terminal. To ship out of Vancouver, you have to go down the Columbia River. It's about a 12-hour run, so it's a half tidal cycle. There's probably about a dozen bridges. It's a lot of scouring activity from the tides and the currents, and it rains a lot in that part of the country, which means you're going to have buoyancy influences on the vessel. Boy, if we had an observing system, And if somebody would develop a predictive capability, you could really help out the shipping community. That's the new blue economy. Well, guess what, folks? It's here. It's here in this form. This is a model output from a service called LoadMax, which was actually developed by the Merchants Exchange out of Portland. And the idea here is that take all those factors that I alluded to, hydrology, oceanography, geology, and be able to provide a really meaningful product. In this case, what you're doing is you're putting in a vessel that has a draft of 42 feet. You're saying, I want to go 12 knots from Vancouver out to the Pacific. That section in the middle shows you will have adequate underkill clearance for the whole cruise there at 42 feet, 12 knots. So it's safe passage, 42-foot draft, 12 knots. Great, you say, I'm the shipper. Remember that, $1 million a foot? I want another couple of $1 million. I want to put a 44-foot draft vessel in. And this is what happens. Minus 0.2 feet is not a good thing for underkill clearance. Your ship's going to run aground. Potential grounding. But is there anything I can do? I still want that 44-foot clearance. And the answer is yes. Under these conditions, it turns out that if you load your vessel to 44 feet but simply slow down to 12 knots, which may sound like a very simple calculation, I assure you it is not, given all of the dynamics going on here, you end up with safe passage again. So the bottom line here, and it takes you, if you were paying attention, that arrival time at Tongue Point is about an hour and change later than it would have been under the other circumstances. You now have a decision aid. You willing to go an hour later, but get additional underkill clearance or additional loading out of the vessel? That is the economic benefit to having the understanding of not just ocean sciences, but certainly the ocean sciences piece of this. So what I hope I've done in the last few minutes in this retrospective is talk to you about the value that ocean sciences has played in what I would argue are three of the critical aspects of society. Lives certainly in terms of our health, lives in terms of emergency management and nutrition, our livelihoods. We haven't talked specifically about agriculture, but I'm sure you can see how some of the forecast capability has enhanced agriculture. My colleague Craig McLean likes to say, if you like your 7-day forecast, thank an oceanographer. There's some merit to that argument. Didn't talk really about the insurance side of things, but I can tell you 20 years ago, the reinsurance industry supported more postdocs in physical oceanography than all of the federal agencies combined, for good reason. They realized they were not mitigating their risk by the way they were investing around the world. So lives, livelihood, and of course lifestyle. Didn't talk a lot about environmental quality or species protection or marine protected areas, but that's obviously integral to all of this. And the fundamental point here is that this doesn't happen without leadership. Leadership, as is in the room here, from the days of William Ritter over 100 years ago to Dr. Margaret Leinen. I would argue Margaret wears pearls better than the others in this particular. And I'd like to spend just a few minutes recognizing what that leadership looks like. It's easy to say, hey, great leaders, that's how these things happen. But what exactly is it? And so I want to take a few minutes and embarrass my good friend Margaret by pointing out that there are elements of leadership. These are like the fundamental knowledges, skills, and ability. One is building a community. And what I'm going to do in the next half dozen slides is show you how Margaret has built these traits into leadership. And the building a community part was so evident in her leadership of the Oceanography Society over 30 years ago now, where if you look at Oceanography magazine, the magazine from the Oceanography Society, you will see that Margaret wrote some wonderful essays, editorials, on the value of multiple constituencies, public sector, private sector, philanthropy, academia, and that it was more than just research, it's also about service. And then I loved the attention to the blue, green, brown water issues as well. This was a time when we were still thinking you are either a physical, biological, chemical, or geological oceanographer. and never the twain, whatever they are, shall meet. This was a fundamental turn for the community. I want to talk about scientific leadership. One of the most influential activities that the US government undertook in years past happened under Margaret's watch as Assistant Director for Geosciences at NSF with the Ocean Observatories Initiative. I would give you the quote that she had from her testimony before Congress, but it basically said, we need to measure the whole ocean, we need to measure all of the parameters, we need to do it in a consistent way. OOI was a trendsetter in the oceanographic community in terms of understanding why some of these very expensive observations were so critical. Let's talk about policy acumen, and I couldn't be happier that Dave Halpern and Rita Caldwell and Margaret and I are in the same room. Rita, I remember the day that you established the Joint Subcommittee on Ocean Science and Technology, and Dave was here. There's Dave. Dave and Margaret and I were co-chairs of that very first committee ever that the US federal government had to address ocean sciences. And really, at Margaret's urging, we went forward with the first definition of ocean research priorities plan and implementation strategy, an effort that's continued for now over 20 years. And it was really, I remember so well as co-chair watching Margaret kind of orchestrate how 13, 14 federal agencies work together. If you imagine having 13 teenagers in your family, that's kind of what it was like. And it was really an extraordinary demonstration of policy acumen and how to work policy. Scientific integrity. I was on the plane with Janice LaChance. Hi, Janice, yeah. I'm going to come back to you in a minute. But the American Geophysical Union, of which Margaret was the president, was dealing with some very sensitive issues. The whole oceanographic, the whole science community was dealing with a range of ethics issues in 2017. And Margaret stepped forward, 2019, and really developed a number of policies tied to ethics, integrity, and yes, diversity, equity, and inclusion, because we were behind the curve in the ocean sciences community, and it needed to be stated. And thank you, Margaret, for stating that so strongly. I think it has had a lasting effect on the scientific community. Initiative, another trait. In 2019, the White House had a summit on oceans and partnerships, and there were a number of things said, but I've run into a number of folks who said, do you remember when Margaret Leinen said, the oceans are having a moment? That message stuck, and it stuck all the way to the White House because that moment was preserved when about a month later the president issued a presidential directive associated with mapping, ocean mapping and charting. The last piece I want to call out is Margaret's role with the United Nations Decade on Ocean Science for Sustainable Development. A title too long to put on a slide, so I just put UNDODSSD there. And in this case, let's go ahead and play this video.
One of my hopes for the decade by 2030 is that we will routinely be making long-term basin-wide measurements of the biology of the oceans to see how the various parts of the ocean interact and how the biology changes with climate and with human impacts on the ocean. We have to know more. We have to understand this great piece of the globe that affects us.
Now you watch that video and you see Margaret's role with the UN Decade, and you might think, well, it was about biological observations. When I heard that video,
one of my hopes for the decade by 2030 is that we will
the emphasis there was on the role of all of our observing partners to work that. So those were just a few of the examples of your leadership, Margaret, and how it's changed the science of oceanography. Thank you for that. I want to break right now and thank Margaret. When I was asked to deliver this talk, I think it was December, a time that I think back now was kind of quaint. And I look at the things I was working on as I was closing out at NOAA and realize now, as I prepared this talk, that it would be kind of tone deaf for me to finish there without recognition of the challenges that we have in front of us, but also try to share with you some optimism and some thoughts about how we move forward. And this is really characterized by a statement many politicians have made: elections have consequences. Sorry, there's no sound on Mitch McConnell, but he's saying elections have consequences. And so I thought, well, what are those consequences? And unfortunately, right now, when you look at it, there have been any number of statements, and I pulled out 3 or 4 of them from recent publications. The first one comes from a faculty member, Fred Allendorf, who says we're entering a dark age of American science that will last for decades. The Guardian put out a story, this is specific to my own alma mater, if you will, NOAA, where thousands more workers have opted to take offers of early retirement or voluntary separations. At NOAA alone, roughly 27,000 years of collective experience was lost in one day. Similarly, the Institute for Macroeconomics and Policy Analysis last month said budget cuts to public R&D would significantly hurt the economy in the long run, with large negative effects on GDP, investment, and government revenue. And then the last quote comes from the CEO of AAAS, who said in congressional testimony last month, unfortunately, the implementation and execution of these efforts, meaning the budget, will dismantle the engine of hope and prosperity for millions of Americans. It would be easy to hang it up, to get frustrated, to walk out, but I want to paint you a different picture. And that picture actually has roots in what happened in this country 80 years ago. In 1941, during the middle of the war, FDR asked Vannevar Bush to start the Office of Scientific Research and Development. That was the office that during the war developed radars, developed any number of systems. And then after the war, just before he died, FDR said to Bush, okay, what do we do now? And Bush, with a small group, prepared a report called Science, the Endless Frontier, which has been the mainstay of our scientific enterprise in this country for 80 years. It was the piece of policy that drove the National Science Foundation Act and established Alan Waterman as the first director of the National Science Foundation, and led to an extraordinary array of leaders, including Dr. Caldwell. It established a way for our government and our nation to move forward and have such a productive next several decades. But you know what? Maybe it's not right for now. And in fact, when I was NOAA's chief scientist, I sat down with my peers from Department of Energy, from NASA, from National Institutes of Health, from USDA, some names that many of you know on this list, and said, should we talk about what the next paradigm should look like? And we ended up publishing a view of what the next paradigm should look like. And so my thesis is this, that 80 years ago, a major crisis led to science, the frontier, the next frontier. We're in a crisis right now. Might we be able to look at this crisis as an opportunity? Fight the good fight to make sure we're getting through, to make sure the students here get a good education, have job opportunities, make sure we retain the best and the brightest in the scientific enterprise, whether in government, academia. But maybe it's an opportunity to talk about what this algorithm looks like. Things like commingling public and private resources, which, oh, by the way, is illegal right now. Maybe it shouldn't be. Maybe we should have ways of taking money from public and private sources. Maybe we should look at academic and government consortia differently. Maybe we should embed academic scientists in the government in ways not like IPAs, not like rotators at NSF, but actually firmly embed, and vice versa. Maybe we should address the risk tolerance within the investments that are made by the government, so that we don't have to say every time we want to do something extraordinary, let's create an ARPA for that. Maybe we could actually build that into the enterprise. Peer review. Maybe there's a better way to do that. I worked at ONR. ONR's attitude always was you hire the peers and have them do the review as program managers. It had its flaws. It worked pretty well. Maybe there's program management ideas that can take these challenges and embody them in a new way forward. And then the thing that I didn't put on here because it hadn't formed in my mind until I ran into Janice on the airplane yesterday was, and oh, by the way, congratulations, Janice, on your appointment as AGU Executive Director. That's wonderful news. And congratulations to AMS and AGU on taking a step forward to ensure that the National Climate Assessment, or something that closely resembles it, is actually done this time around. Thank you. And the lesson learned from that is maybe there's a role for the professional societies that we are all part of. Some of the leadership of those societies is here in the room. Maybe there's a role that's different. And AGU and AMS are showing us examples of how to do that. But let's look to other professional communities, including the ones that we're not necessarily involved with. What are they doing? And how might we change it? So I will continue to be optimistic that how we do our science and the future enterprise is going to be in a different mode. And it's up to us now to identify those end states that we think would be worth doing. But let's not lose sight of the fact that there's still some really exciting scientific and technical stuff out there. And again, we could spend the whole day, and we will spend a lot of the day talking about these kinds of things. But I will tell you that when I left NOAA, there was a lot of discussion about the use of AI, mostly ML, large language models, for a lot of the weather data and that kind of thing. And what I kept saying is, yeah, but what about the Gen AI side, where, for example, if you want to put a new regulation in about fishing, it's going to take you 3 years because it takes thousands of hours of review of the literature, thousands of person hours to review the comment period comments that you get in there. Maybe there's things that we can do with Gen AI in the scientific community. We've talked about observing systems, we'll talk more today, but the idea of resident, persistent, adaptive, smart observing systems, so that we don't have to say, hey, let's go launch some gliders because we see a tropical storm forming, that we actually have a system embedded on the East Coast, the West Coast, the Gulf, the Arctic, that are smart enough to say it's time to go sampling, launch 1,000 autonomous vehicles, make observations, talk with each other, sample smartly. We're really close to that. I got to thank Marcia McNutt, my friend, the president of the National Academies, for this concept. It's not quantum sensing. No, that's not a typo. Quorum sensing. Quorum sensing is basically the idea that microbial cell-to-cell communication can actually translate to changes in gene expression. Can we use that as a means to sense the environment in ways that we haven't done before? And then managing the ocean commons is kind of a big catch-all. Jack Dangermond, the founder of Esri, has said we need an ocean GIS. Well, it's not just to have a GIS. What Jack's talking about is if we're going to talk seriously about deep sea mining, if we're going to talk seriously about marine carbon dioxide removal, if we're going to talk seriously about ending illegal, unreported, unregulated fishing, you better have the data systems, the interoperable, layered data systems, and a lot of that is in the ocean commons. So I didn't want to end with a downer, but I wanted to end with the idea that there's so many exciting things out there from the organizational standpoint, from the community standpoint, and from the scientific and technological standpoint, that I, for one, am optimistic that if we can get through the current crisis, we have nothing but the sky as our limit in terms of moving forward. And recognizing that we have such extraordinary leaders in the community, like you, Margaret, I'm further emphatic in my enthusiasm for what is going to happen over the next 20, 30 years. Thank you for the opportunity. I really appreciate it. And Margaret, thank you for everything you have done for the community. Q&A?
thank you, Rick, for that awesome talk. We have time for a few questions, if there are some. 2 minutes we've got for questions. See, over there?
Perfect. Yes.
Perfect timing.
I used to work for an admiral who, when you had this sort of embarrassing silence, he would pick on someone.
There are no graduate students that I can identify, unfortunately. But I was, yeah, go ahead.
Thank you for the talk, Rick.
Thank you, Paula.
Sorry. You have my mind, churning on this idea of a global observing system. And I wonder if you could say something about, maybe the industry and other partnership opportunities. You touched on the academic government one, but I'd love to hear a little bit more about your thoughts there.
Yeah, thank you for that, Paula. Yeah, industry's got to be a key player. When we started talking, and I love that you raised this question because URI has been a leader since the time Margaret was there on this, incorporating business, the blue MBA ideas, that industry's got to be a part of this. And I would argue that in the past years, we didn't have the technology. Industry said, hey, you got some catching up to do. We can't do the observations in a credible operational way. We have that now. I know that we have that now. And I think the challenge for us is the capital. Where is the money to do this? And so some of the things that have been done that we did at NOAA with accelerators, for example, is the way to get that done. But it means getting out to the investor community in ways that other scientific communities have done so. I think that's the key. That'll break the code. Because there is, be crass about it, there's a lot of money to be made.
Okay, I'm getting the signal from Kayla over there. Thank you so much,
Thank
Rick.
you. Appreciate it.
Great. My colleague Chris Charles is now going to take over for a session on marine sediments.
Yeah, thanks, Cathy. So for those of you who don't know me, I'm Chris Charles, a faculty member here at Scripps, and I will be the moderator for the first of 3 sort of science-based sessions. So as we've already heard, this sort of arc of past, present, and future of oceanography can be applied to the discipline as a whole, or could be applied to specific scientific pursuits within oceanography, and it could also be applied to Margaret's own career arc. So that's sort of our vision as a organizing committee for this, the organization of this symposium and the series of panels. So what I will be doing is moderating the session on sort of the past of oceanography, and in that sense, you could kind of think of me as the ghost of oceanography past. This is, Margaret, as you've already heard, sort of began her career thinking about and interrogating the seafloor, and specifically the changing mineralogy and patterns of mineralogy of seafloor sediments, to say what those patterns and trends could tell us about ocean processes, the evolution of the interaction between, say, dust input to the ocean, changing patterns of winds and that effect on the upper ocean circulation and the fertility, changing fertility of the oceans as reflected in the biogenic minerals. So that's the so-called discipline of paleo oceanography, of which I'm a card-carrying follower, I'll put it that way. So Margaret may have moved on from that to other things in her career, but what we hope to show with this panel, or demonstrate with this panel and series of talks, 3 scientific talks, is that the discipline of paleo-oceanography and the pursuit of interrogating the seafloor for its history of ocean climate and life in the oceans is certainly not a dead science. And in fact, we kind of very much want to impress upon you the notion that in line with William Faulkner's famous quote from Requiem for a Nun, the past is never dead. In fact, past isn't even past. So that concept can be applied. Well, so Faulkner was talking about the lasting presence of and influence of original sins of American Southern culture, but you can certainly apply that in a scientific way as well. So as we will hopefully see, not only are there important lessons to be learned from continued interrogation of the marine sediment archive of ocean history, in terms of case studies for enlightening present ocean processes, but in fact, there are important feedbacks, slow feedbacks, and geological processes that are impacting our present ocean processes in a major way. Sea level change is a prime example of that. So that's the idea, and so again, we'll have a series of 3 science-based talks, and then Kayla's giving me, wrap it up. And then a break, and then a panel discussion that reviews challenges, opportunities, and priorities. I will ask that we hold questions for the individual speakers until after the coffee break, just to make things more efficiently. So with that, let me introduce the first speaker, who may be familiar to you Scripps old-timers, Tim Herbert. So Tim was an assistant professor here at Scripps in the late 1980s to 1995. He since moved to become the Doherty Professor of Oceanography at Brown University. And for 40 years, he's been fighting the good fight of interrogating the seafloor for its record of evolution of ocean change. And so, Tim, we're happy to have you give your perspectives on that long career of struggle.
Oh, you're going to do that. Okay. There you go. Put this down and then you'll be a bit more stable.
Well, thanks so much for inviting me here. There are all kinds of good memories I have from my time at Scripps and people who are still here who I value. I learned a tremendous amount while I was here, and I'm really happy also that being here allowed me to think back about Margaret's career and the field that I love of paleoceanography and to reflect on it a bit. So when I think about the contributions, I was reviewing some of Margaret's work, and some of these papers were absolutely embedded in my brain as a PhD student. I can tell you a few of these figures I would just think about all the time. I think what Margaret and her colleagues, did, what happened here? Oh dear. Help, I don't know how I got out of PowerPoint, sorry folks. Yeah, I know. Right, as Chris said, in 40 years, it's still happening, but yeah. Chris, can you give me a hand? Sorry, I don't know how I did this.
Oh, okay, you need to navigate over here. So where's the cursor? Ah, there it is. This way, this way, this way, this way, this way.
Thank you so much. All right, hope I don't hit the wrong thing again. What I think Margaret and her cohort did that the rest of us have benefited from tremendously in paleoceanography was to bring climate and oceanography to marine geology. And that sounds like a simple thing, but it's not at all. And so the imprint of climate and the recognition that patterns of wind circulation and dust, I think we'll hear some more of that from Gisela Winckler soon, are imprinted in the seafloor and the record of sediments. And on the right-hand side, the record of biological activity is recorded in ways that are critical to understanding how the ocean's biosphere changes to past climate changes. It was really bringing climate into the study of the past that was essential, and that set the mark for where those of us are working now. And in particular, I want to point out that these studies did something critical, which was to ground what we see in the seafloor and the past in the present, in what's happening, and to calibrate it and validate it. And that approach is really critical to trying to understand the Earth's past in a more meaningful way, in a way that actually ties the paleo and oceanography together. All right, so cannot tell this story without something that's on the minds of many of us in paleoceanography. The long, distinguished career of deep ocean exploration by the JOIDES Resolution, and before that, the Challenger. Margaret, part of her career, were leading expeditions and being involved with exploring the Blue Sea with a capability. It's a capability we've now lost, and I think an important question for the future of marine geology, marine geoscience, is the need to replenish, regenerate the capability of the ship. I'm just showing on the left the pay dirt that you get with this capability. These are deep sea sediments recovered off the coast of Portugal. They're about 3.5 million years old. They take us back to a time where there was probably no Greenland ice cap. Sea level was 100 meters, about 25 meters higher than today. These sediments are recovered more than 300 meters below the seafloor, but they look like they've come up from yesterday. You see the burrowing structure for organisms stirring the mud back in the past. And it's this technological, logistical capability that lets us read these layers recorded back to reconstruct what the oceans and our climate have been. You can see very evidently the record from the ocean as the climate changes. Those are cycles that relate to 20,000-year cycles in the Earth's orbit that trigger, mysteriously, changes in the oceanographic setting. So I wanted to try to take some of the work of my group and pose a focus question. It's a question that relates to so much of Margaret's career, which is spent studying the Pacific Ocean in different aspects. And it's asked the question, as we go back in time with this capability, can we think of the long-term evolution of the eastern tropical Pacific in the way we think of modern climate variability with the analogy of the El Nino cycle? That is, that the ocean can be in an El Nino or La Nina state. Is this a good way for understanding the long-term, the deeper history of the tropical Pacific Ocean? You might guess I'm going to say no. All right, so there are many people I want to acknowledge who worked in my group over the years that have contributed to this. Here are a few. And as you'll see, the strategy I'm going to use is to use the capability of generations of ocean drilling to look at a transect of sites that take us from near the coast of South America out into the central tropical Pacific. I'll only be featuring a few of these for the length of time. And I want to remind you, we're looking down today at sea surface temperature. We chose this transect because it's a region today of very intense gradients in surface temperature, in wind stress, in biological activity, and of course we know that those vary very dynamically at the ENSO timescale today. So I think many people have seen this sort of cartoon of these two end-member states that characterize El Nino that reflect interactions with the air-sea interface, exchange of momentum, precipitation with water, wind stress, heat. And this has been the guiding metaphor for a lot of paleo studies, that this is the way that the Pacific Ocean changes, and it may be more or less in this state. Increasingly, there's work thinking about the link of these tropical dynamics to regions farther flung in the world. So here's an example of looking at changes originating at much higher latitude and how they may interact with the ENSO cycle. And increasingly that work is also recognizing subsurface processes. It's not simply what's happening at the air-sea interface. And here's one example of George Philander and a colleague pointing out the importance of subsurface flows in determining the characteristics of the Eastern Tropical Pacific. George went on to give me a direct link to what I'm going to show you today by posing the question between long-term geological change and the evolution of the Eastern Tropical Pacific. And what George and Alexei Fedorov propose is that, as you'll see, the Earth's climate has cooled significantly over the last 3 million years. And that cooling has been more intense at high latitude than low latitude. And they propose that this long-term change would show up at the heart of the tropics, the heart of the tropical Pacific, in the Cold Tongue region, by what's called the oceanic tunnel that brings water from far away, mostly from the subantarctic mode water, but also North Pacific, and in fact forms the base of that thermocline layer that gives chemical and physical properties. And they propose that long-term climate change might act through this tunnel rather than directly through air-sea interactions that we know characterize El Nino today. So we're going to look at that picture cut down to emphasize the interactions up at the surface between the wind, sea surface temperature, momentum, but particularly that red arrow, which reflects the very complicated trajectory of water from high latitude that eventually forms the base of the thermocline underlying the Eastern Tropical Pacific. And we're going to do that from sediment records in that transect that capture various aspects of this picture. An important thing to remember, one of the beauties of marine sediments, they integrate lots of different kind of information that is co-registered, that occurs in the same material. So you can monitor different aspects of the ocean in the same sample, meaning that the chronology isn't really important. You can measure the response of one compared to the other. And so let's look at what I'll show you, I hope succinctly today, that we'll travel back in time a little more than 3 million years ago to look at this long-term evolution, ask the question, can we look at it as essentially Earth moving from one state, El Nino, to another, La Nina, and more persistently, or is there another message that emerges? So we'll look at sea surface temperature, a critical component of those gradients today, interaction between the air and the sea. And we'll do it from a tool that my lab has worked a lot on, records made by marine coccolithophore algae that live at the ocean's surface. They're photosynthetic. And they make hard parts, but we actually use biomolecules made only by one closely related family of coccolithophores that miraculously contain in their molecules a record of the temperature at the time they lived. And they live today, they actually can be grown in the lab, and you can make the water warm or cold and monitor the response. And those two peaks you see colored actually provide strong constraint on the temperature at the time they live. These molecules are formed in the surface ocean. Organisms die, fall to deep sea. They're preserved for millions of years. We can also look at to probe the subsurface structure, critical to think the contrast between the thermocline and the surface. Planktonic foraminifera, one-celled animals that make a carbonate shell. And we can look in this case at a species on the left that lives very near the surface, a species that lives down in the thermocline, about 100 meters. And we have isotopic recorders that give us an indication of the temperature difference over that 100 meters, and also differences in dissolved inorganic carbon, a clue to the nutrient properties of the water. And lastly, in the same sediments, we find the remains of organisms that live at the bottom of the ocean, 3-4 kilometers depth. And they provide us with this timeline that captures the Earth's climate change over, in this case, the last 5 million years. So 0 is today, 5. And I've learned from my students that wiggly lines don't always instantly excite everybody. So just let me think of a metaphor that I use. We're looking through time at what you could think of as the heartbeat of one aspect of the Earth's climate. These isotope data record oscillations of warmer ocean temperature up and high sea level, the melting of glacial ice caps, on the low end, cooling of ocean temperatures, formation of large glacial extent that lowered sea level. And if you were a doctor, you'd look at these and you'd look at the frequency, how often is the heartbeat going, and you look at the amplitude, and this is how we look at climate change. So this summarizes an early period where the climate changes were subdued. And as we move toward the present day, the changes have gotten steadily stronger. We don't fully understand why. They've also changed in rhythm, how often they happen, and that's another interesting story. So we'll be looking at the evolution up there at the surface in relation to these global changes. All right, so first question. If you looked at that diagram, you might have seen that the frequency of ice age cycles has changed. Back between 1 and 2 million years, the amplitude was smaller, and they were more frequent. And they've grown to be larger and slower as we move toward today. So the first question we ask is, as we travel back in time, how has that pattern up at the surface of ocean temperature changed through a major transition in the Earth's past climate? And I'll take you very quickly to the summary. The center panel shows the evolution of the last 1.7 million years. 0 again is today, 1,600,000 years, 1.6 million years. The central line is our estimate of sea surface temperature from those algal remains. The blue is the oxygen isotopes. That's a global monitor of climate. Down is glacial, up is interglacial. The green line, inversely plotted, is the amount of the organic compounds in the sediment, a clue to biological activity. And I'll just direct your attention to the top panel, the most recent 600,000 years. You can see the temperature and global change recorded by Delta 18 are very much in sync. The cycles are large amplitude and relatively slow. But what got interesting to us was the bottom panel, which zeroes in on that time of smaller and more frequent ice age cycles. And remember, we're right at the heart of the equator at this site. So the annual insolation driven by the Earth's obliquity cycle, which is an important component of what makes those ice ages come and go, is highlighted here. And in the tropics, the obliquity cycle actually regulates tropical annual heating. When we compared that to the response, what we see in the record is that the temperature here at the heart of the tropics is actually antiphased to the insolation at that frequency. In other words, these changes cannot be driven by local changes in the radiation budget. They're imported from high latitude. When we look at the ups and downs, this is a detailed record. The upper panel, the Delta 18, the middle, the temperature. What we found, if you look down to the green line, is that these fluctuations in temperature map to the fluctuation of a species that indicates shallow and deep thermocline. So the thermocline is dancing up and down, and when the thermocline is deep, productivity is low. When the thermocline shoals, like we might expect. So we see this ancient dance of thermocline and temperature playing out in the past, but dictated by processes not local, but remote. All right? So we've gone through that change. One key monitor shows that the tropical Pacific is highly sensitive to one of the major global changes in climate that happened from 1.2 million years, 1 to 2 million years to today. Let's look at another milestone in the evolution of Earth's climate, a larger change. The purple line there shows the descent of the Earth's climate into the current ice ages. That intensified about 2.7 million years, and since that time we've had large ice in the northern hemisphere, large advances and retreats of ice age cycles, very large global changes in climate. And again, we wanted to know, how do these manifest in a region so remote from ice itself? So we assembled at the site near just to the east of the Galapagos one of the longest records of past sea surface temperature using those algal remains. 0 on the left, 4 is 4 million years ago. And we see a lot of variability in the heart of the tropics that turns out to be synchronized, those global changes, the ice ages. And features turn up such as the intensification of temperature variations coincide with the appearance of ice rafting in the North Atlantic and other climate milestones. To our surprise, when we compared these records to other tropical records, we thought, maybe the EEP is its own animal. They look strikingly similar. The pink record is just one of many I could show you taken from the Indian Ocean overlaid. So the EEP, although it certainly has its own characteristics over time, the cooling is more intense and higher amplitude, is part of the global change. It feels the global change that affects the entire temperature of the tropical ocean over the time of these ice age cycles. Now I'm going to take you a little bit into the question of gradients. We know that today the eastern tropical Pacific has very strong gradients in temperature biology. How has that been in the past? The upper panel shows you in blue a site to the east, in the heart of the cold tongue, just east of the Galapagos. In the red, well to the west, 117 degrees west. And we see the evolution through time, 3.5 million years, 3,500 kiloyears on the right, 400 kiloyears to the left. We're seeing there's discontinuities because we don't have the entire record done, but we're looking at windows of time. We see that the EEP has transitioned from its present very strong east-west gradients, if you look to the left of that panel, 3-4 degrees over a few thousand kilometers. But as we go back in time to a time before the ice ages, the gradient nearly disappears over this entire lengthy span of the Pacific Ocean. So as climate warmed, thank you, Kayla, those gradients weakened. So we know that the cold tongue is really a modern phenomenon. And we also found that the subsurface temperature gradient has strengthened toward today. So that sounds like El Nino, right? Strong gradients, strong and cooling patterns, but not so fast. When we look at biological activity, we get a very, very different picture. Again, we're looking at snapshots through 3.5 million years at ways of estimating biological activity. We see, in fact, that biological activity in the eastern part, the heart of the cold tongue, has hardly changed over 3 million years. It's ups and downs. While toward today, it's actually weakened, that's the red curve below, at the same time that temperature gradients have increased. This is not El Nino. And that's verified by a proxy that Margaret used, and one of the ones that was burned into my mind as a graduate student, biogenic silica, a different biological group. Again, about 3.5 million years. We're looking at 4 sites here. Just to cut to the chase, look at the lower panel. The blue represents sites to the east. It's always been more productive, like today, with more upwelling. But the pattern of opal accumulation was actually much higher during the warmer past than during the current cold, intense regime. All right. So what do I think is happening? We've seen that the eastern tropical Pacific warmed a lot in the past, and that gradients in the thermocline weakened. That sounds like an El Nino. But at the same time, biological productivity was, if anything, stronger. That's not El Nino. And I think one thing we have to think about in the dynamic that will play out over the next decades is that the subsurface temperatures play a critical role in density stratification, the work the wind has to do. So there's a yin and a yang between winds at the surface responding to global change, but the subsurface density structure that affects how much work the winds can do. So what I've tried to show you is that we can investigate the past plumbing of the modern El Nino system, both at the surface and subsurface. That change in the cold tongue, in fact, is amplified relative to the tropics, but still coherent with the tropics. But that when we look at the biological consequences, which of course have enormous impact on fisheries and other things, this does not follow what we see on the timescale of ENSO. And to me, this is one of the values of paleoclimate. We see long-term adjustments in the Earth system that we may not see in a decade or two of monitoring, which focus largely on the fast physics processes of exchanges at the sea surface. And therefore, as we go into our future, the evolution of the waters feeding the eastern tropical Pacific, that ocean tunnel, waters formed mostly in the Southern Ocean, but also in the North Pacific, will be critical on timescales of decades or centuries, and that's what I think we see played out as we investigate the Earth's deep past. Thank you.
Okay, yeah, thanks very much, Tim. That was great. So as I mentioned, I'm sure you have questions, but hold those thoughts, and you can ask them either during the coffee break of the individual speakers or during the panel session. So our next speaker, it's unfair and reductive to refer to anybody as Margaret Leinen 2.0, so I won't do that, but I will say that if you could think of one person that is the international recognized leader in many of the early pursuits principal pursuits that dominated Margaret's early career, it would be our next speaker, Gisela Winckler, who is a professor of climate at the Lamont Doherty Earth Observatory of Columbia University. She is an expert in using the geochemistry of marine sediments to understand past changes in wind fields and dust input to the ocean, exactly as in line with what Margaret started. She was also recently co-chief scientist of IODP leg 383 in the Southern Hemisphere that was dedicated to those themes, just very similar to Margaret. So I think we'll hear some of the fruits of that expedition, along with maybe other general perspectives.
Did work already, huh? Right, let's try that again. Actually, is the HDMI? Yes, excellent. All right, thank you. Thank you very much, Chris. You know, I'll take Margaret Leinen 2.0 any day. So maybe I'll add it to my signature. I hadn't thought of it that way. But thank you very much for that introduction, and huge thank you for having me here today, because it's really exciting to be here and to be part of the celebration here today at Scripps. And so Chris actually asked me to talk about the early work that you have done on marine sedimentology, and particularly on dust. And this is what I will do, you know, based on that lovely introduction. And I'll try to highlight also these connections to where we are today and how that sort of evolved over time. And particularly the idea of using dust in sediments to trace something as elusive as winds and atmospheric circulation, which sounds crazy, right? How can we do this millions of years ago? But also the impact of dust and ion input on ocean chemistry, on the carbon cycle. So I'll show you a couple of these examples. And, you know, as I said, it's truly an honor to do this. And that is partially because of this groundbreaking work that allows us actually to sort of figure out these systems and essentially underlies our understanding today of these connections between aerosols and dust and climate. And the other piece in this is that I've actually always had, I'm probably one of the people here in the room, I should say that, who has the least personal connection. You know, I've met you a couple of times in the past, but I don't have a long shared history. But I've always had this deep respect and appreciation for you and your work, and this is essentially sort of a puzzle of many, many different pieces, small little pieces, but very meaningful to me. And one illustration of this is actually this photo. This is Cristina Ravello from UC Santa Cruz and I on our first day of this expedition 383, sailing through the majestic Strait of Magellan. I had never been on the JR, but I got selected to sail as a co-chief scientist, for which I was really grateful. Think of someone who has zero experience on that ship, but still sort of gets the honor to lead one of these expeditions. And on this expedition, I learned a ton through many, many, many conversations from Cristina Ravello. And really, you know, she helped me a lot sort of in the early days of sort of figuring out the ropes of how to do this, how to actually lead an expedition on the ship. And I'm saying this because in these conversations, she always told me about her first experience on Lek 138, which we saw earlier in Tim's talk, and we'll see later today, where you were the chief sedimentology person in the night shift, and Cristina was your mentee, and, you know, she told me that you called yourselves the Lady of the Nights. Because in the day shift, that sedimentologists were all men, duh. And so it's these stories and these pieces of, mentorship that you've given others, that have always been very meaningful to me. And so that's why it's really an honor, to be here and to be part of this day today. Yes, so dust. What do I mean with dust? I have actually two introductions of what I mean and what I sort of connect with dust. The first one is perhaps a little unusual. That is this beautiful work of poetry about dust by Agnes Den called The Book of Dust. I love the subtitle that is The Beginning and the End of Time and Thereafter. And whenever I have one of these moments, I actually look at this book and love it. It also has this beautiful definition: dust is particulate matter, the dispersed, disordered raw material from which everything ordered and coherent arises, and it is to dust that the complex decays. Much more elaborate and poetic than what I do sort of in my day-to-day life, where I more use sort of the classical definition of dust. I want to show you here this simulation and just run it for a moment. Oops, no. Yeah, so this is actually simulation of all types of aerosols swirling around the world. The dust is these orange and red colors. This is the mineral dust from the vast deserts on the planet that gets picked up and swirled around the world. So this is the dust, or the imprint of that dust deposition in the marine sediments that we will be talking about here. And dust research is not new. It didn't start with Margaret. It actually started way earlier, and this is this beautiful example of the work of Charles Darwin on the Beagle. So I go back even longer than you did earlier, I think. This is 1832. When Charles Darwin in his diaries actually describes this moment where they were in a dust storm that actually destroyed some of their instruments. I love the second part here where he talks about collecting a little packet of this brown-colored fine dust. This is actually one of the samples from the Beagle that still, research is being done on. And essentially, this is what we do 200 years later, right? We collect little packets of brown dust. In our case, we extract them actually from marine sediments. And then, of course, there's the pioneering work by Margaret. These are a few of my subjective collection of these papers that I also found really inspiring when I started doing this work in the 2000s. Some of them overlap with the one that Tim picked. And I'm just showing you here sort of the first. This is from a paper in 1985, the first records of the dust flux, the mass accumulation rate of dust. The one in the center actually goes back the entire Cenozoic, 65 million years, and it's based on these two cores from the North Pacific that we will also see later again. And the one on the right is the more recent history, the last 800,000 years going back in time as you go to the bottom of that graph. And that was the first sort of glimpse that we had. We now have a refined picture of those dust flux records that I will share with you. And sort of in general, because I think the theme is much bigger than just looking at dust for the sake of dust, right? What we really want to do is learn about the climate system. And there's a whole variety of ways of doing this. This is my categorizing, essentially, what we can learn from the imprint of dust from marine sediments. And I'll show you two examples here today. And the first one is really about these direct impacts on the climate system, on the radiative balance of the Earth. How does that work? And how does that relate to climate change? And what can we learn from this? The way I do this today is less with mineralogy, but with isotope geochemistry. So I use uranium thorium, not just I, my group, and many other groups used uranium thorium series elements that are measured with ICP-MS. And sort of the beauty of the thorium isotope system that I happen to use is that with one measurement, you actually get two things. You get a proxy directly for the dust itself in the sediments, and you get a proxy for the total flux, the total accumulation of material. So most of what I show you is based on this idea. And I'll show you a story of the Pacific, of the tropical Pacific, very closely without actually planning this out, related to what Tim showed. From these 3 sites in the equatorial Pacific here, why those 3? One is PC-72, my favorite piston core of all. And that is actually from the Jacobs transect in 1991 or 1992, long before my time, that Margaret led. And as Bob Anderson always says, you know, these are the best cores that we have, and that's not just sort of coincidence, it actually is because you knew what you were doing and you had sort of put all the thought and research into coring at the right places with the right people and getting these really beautiful piston cores. So this is the one in the middle here in the central equatorial Pacific. The one on the right, on the east side, is ODP 849, which is one of these leg 138 cores that I talked about earlier from the Droides, where you were the lady of the night. And then the western one is INDP 74. I don't know if you were connected to this. If so, then I would know. And so now we are looking at these 3 sites across the tropical Pacific, and we are actually looking at dust flux reconstruction. The black line here, without going into much detail, we are looking from today, 500,000 years ago. The black line is this benthic delta 018 signal that Tim also talked about. That's our measure of climate, of the world going through ice age cycles from warm to cold, from warm to cold. And the red line is the dust flux record as reconstructed from this thorium isotope idea. And you can see that for each of these sites, there is a very strong correlation between climate and the dust flux by these 2 curves following each other very, very, very closely for each of the sites. And so that was sort of the gist of that work, that the dust flux is highly correlated with climate, not just at one position, but across the entire tropical Pacific. And then the next obvious question was, is that only regionally true, or is it actually also true globally? This is, again, that record from the central equatorial Pacific. And now we are comparing that to, as far away as you can think of, to the dust flux record from the ice core in East Antarctica, EDC. And again, we find for these completely different sites where the dust in Antarctica doesn't know anything about the dust in the tropical Pacific, we find this highly coherent signal between the 2. And this is not just true on these glacial, interglacial timescales. It actually is true on these suborbital timescales, which you can see here when you zoom in on the past 80,000 years, that those 2 systems are related. It's the same signal that we are picking up, the same pacing that we are picking up at these 2 different places. When this paper came out, Margaret actually called me, one of the very few sort of out-of-the-blue calls that, you know, I get. And, you know, there was a bit of debate also, right? Now, we didn't always agree exactly on everything, but then after that call, she actually sent me this email, which, you know, I really appreciated at the time, where she did actually agree that, you know, the similarity is really fascinating between these 2 cores, which was really meaningful, you know, because often you are sort of in these, on the joint team with the people who you work directly with, and it's meaningful if it's someone who sort of, you know, does something completely different at the time. So the big question is, right, this is just the dust for the dust, you know, but does it have an impact on the climate system, and how does that impact look like? So we also looked at that question. Is there an effect on the biological productivity, on export production, on the drawdown of CO2 through fertilizing the equatorial Pacific that's iron-starved? So the idea is that additional dust brings in additional iron and actually fertilizes that part of the ocean. And we can look at this by now comparing the red, the dust flux record, with a record of the export production for these 3 sites. And when we do this, this is the blue. There's a lot of debate about what exactly to use for paleoproductivity. I'm using here excess barium flux. And now you can ask yourself again that question, right? The red and the black lines look exactly the same. Does the blue line look like the red? It doesn't. There is actually no correlation between those 2. You can do this mathematically by looking at the direct correlation between those 2 measures, between blue and red. And again, you just see sort of a cloud of points and no correlation. So we, together with other work that's been done along the Line Islands, in this work by Cassandra that I don't have time to go into. Cassandra Costa is now at Hui, sort of found that there is actually productivity is not correlated to dust over these timescales, not on shorter timescales, not on ice age cycles. We don't see that response to the greater supply of dust. And there is the tropical Pacific is wonderful and beautiful in many ways, but it doesn't drive global CO2. There doesn't seem to be a sign of iron fertilization here. And so 2 minutes, oh la la. So my second example is the winds, you know, this idea that you had already way back. We now, and this is what I want to show you, do it a little differently with a little different idea, not so much the grain size, but actually by looking at transects, of course, and particularly this is about the westerlies, these winds between 30 and 60 degrees north and south that are important for us, for humanity, for everything that's actually happening on this planet. They particularly important for precipitation, how much it rains and where it rains. We know actually from recent observations from satellites that the westerlies in the southern hemisphere are moving polewards. And the question that we wanted to ask here is actually, you know, what do the northern westerlies on the northern hemisphere do? And there, the wonderful detailed observations that we have from satellites are actually not clear because there's so much noise in the system. I'm running through this. This is the work by Jordan Abel, who Tim was also involved in this. And I just want to show you sort of the idea. We are back again in the Pliocene, in this warmer time period 3 million years ago. And what Jordan did very creatively is he looked at two sites from the North Pacific, the green and the blue dot that are 9 degrees removed. And he asked that question, can we actually see a shift in the westerlies from that warmer time of the Pliocene to the colder time that at 2.7 million years with the intensification of the northern hemisphere glaciation. These are his records, and you can already see that the blue record, the southern side, looks very different than the green record here, the northern side. And now we are on this longer time scale going from 4.6 to 2.4. Nothing happens through the Pliocene, so the first 80% of all this work that he did in the lab. But then it actually does happen at 2.7, and the southern side here sees these huge swings and huge jumps with that intensification of the northern hemisphere glaciation. Nothing pretty much happens at the green side, and the only way of explaining this is actually by a shift in the westerlies from a position that was more poleward during the warmer time to one that was more equatorward, so southern in this colder time post 2.7 million years. And so we are doing this work not just from the Pliocene into the Pleistocene, but now also through the last glacial cycle where we probably care even more in the Tasman Sea. This is a current PhD student's work, Aviva Infeld's. And so this is a new way of actually looking at this elusive thing in the climate system, at the winds and how they move and why they move and how dust can actually tell us about this on a variety of timescales. So with that, I'll end and thank you very much.
Thanks, Gisela. So our next speaker is maybe slightly different from the themes of strictly paleoceanography. It's someone who, for those of you less old-timers, may here at Scripps may look familiar. He's a proud alumnus of our department here. It's Evan Solomon, who was a PhD student here working with Miriam Kastner. And he's now a professor of marine geology and geochemistry at the University of Washington. And he will be telling us about the sort of interaction between the ocean chemistry and biochemistry and the seafloor in I don't want to do that. Go ahead. Okay. Never mind. I should shut up.
I was trying to be efficient, but I screwed it up. So go ahead.
Okay. All right, I will shut up because his title is plainly apparent to you all. So anyway, Evan.
Okay, no worries. Thanks, Chris. Sorry, I was trying to keep us on schedule. And also, I think I have too many slides. So I was like, oh, we got to get this started. I want to apologize first. I had a family emergency this week, and I've been in and out of the hospital, so I made this talk in the hospital this week. So it's not as polished as I'd like it to be. But the most important thing is I'm here. So it's an honor to be here. I really want to thank the conveners for inviting me. I was a graduate student here, as Chris said, in the 2000s. I studied under Miriam Kastner, and I also learned a lot from Joris Gieske's. This is kind of a chemical oceanography heavy talk, and my first chemical oceanography course was taught by Lahini. It was her first time teaching it. And Cathy Barbeau, she's here as well. So really, it's just fantastic to be here. So what I'd like to talk about is silicate weathering in marine sediments and its effect on seawater composition and potentially the carbon cycle. This is a very old topic. People have been trying to understand the sources and sinks of elements in the ocean forever, and the role of marine sediments in controlling the element composition of the ocean. So I'm going to talk a little bit about that today and work that we've done in my lab, as well as work that other groups have done as well. Okay, so I just kind of want to start from the beginning. Like I said, this has been an old question, and so this is all tied to the geologic carbon cycle. So to the right is a schematic showing the main sources and sink of CO2 from the atmosphere over long time scales. So CO2 comes in the atmosphere from metamorphism and volcanic processes, both in subduction zones and at mid-ocean ridges. And the ultimate sink of that CO2 over long time scales is silicate weathering on land and also carbonate weathering on land. And the precipitation of those cations that are stripped from silicate minerals as calcium carbonate that then is deposited in marine sediments above the lysocline. And so that's what's shown there is water and CO2 acting to dissolve silicate rock, and this is the Urey reaction that Harold Urey developed. And so that acts to weather silicate rock, and you then strip cations out into the ocean. And so using wollastonite as an example, 2 moles of CO2 are used to weather wollastonite. You convert that CO2 to bicarbonate, so that's a generation of alkalinity and calcium. Those ions go with rivers into the ocean as dissolved components, and then organisms precipitate their shell of the calcium carbonate, releasing CO2, and the net reaction is that you're continuously removing a mole of CO2 from the atmosphere through silicate weathering coupled to carbonate deposition. Over long time scales, something like 50 to 70% of the CO2 emitted to the atmosphere through volcanic and metamorphic processes is removed through this process. The other CO2 over long time scales is removed by particulate organic carbon burial. Okay. The figure to the left is a more recent figure by Essen et al., 2019, also highlighting that there are processes where silicate minerals also interact with seawater in the marine environment and either dissolve and precipitate clays or take up clays directly. And those two processes are forward weathering, which is exactly the same as weathering on land, and reverse weathering, where you have a cation pore particle or just solutes from the pore water precipitating clay and taking cations out of the ocean. Okay. The chemical alteration of these turgidous particles in the ocean is largely ignored in standard models of ocean and climate evolution, but they're there, they're reactive. There's a big part of particulate load in the ocean, as we've just heard from other speakers. So in this talk, I'm going to review recent literature and stuff that we've done on the role of marine silicate alteration in regulating the major element composition of the ocean and possibly the carbon cycle. Before I do that, I need to give a couple definitions, just because I'm going to mention it a lot. So 2 things that we measure are dissolved inorganic carbon, which everybody's familiar with, and so that's CO2, bicarbonate and carbonate ion concentration. But I really want to focus on alkalinity. I need to give a definition of alkalinity. So alkalinity is the excess of proton acceptors in the solution over donors. And it plays a major role in ocean chemistry, particularly buffering the pH of the ocean and calcium carbonate precipitation and dissolution, and it plays an important role in absorbing atmospheric CO2 increases and regulation of Earth's climate. So understanding the alkalinity budget of the ocean is really critical. The way we typically measure this in pore water and seawater is by titration, and so this is what we get when we titrate for alkalinity. And I think most people, at least the chemists, are familiar with this, but in pore water systems, ones that are 2 components that aren't that important in seawater is ammonium and bisulfite concentrations can get very high in pore water systems. They're highly variable, and they contribute a lot more to alkalinity than you would think. And so when looking at these alkalinity profiles in pore water, just keep in mind a considerable amount of that is tied to anoxic degradation of organic carbon, producing ammonium and bisulfite. Bicarbonate and carbonate ion concentrations are also highly variable in pore water systems, and so these are the ones that are most variable. Okay, so I want to take a step back and talk about element budgets in the ocean, particularly for the major cations. And so really early work in 1966 by Mackenzie and Garrels attempted to do a mass balance of solutes going to the ocean from rivers and then the output fluxes of those solutes to see how, well, to determine the sources and sinks of those elements in the ocean. I'm not going to go through the details of those calculations, but I just want to highlight that though in 1966 the riverine fluxes of the major elements in the ocean were pretty well constrained, the output fluxes certainly were not, okay? And this is before the discovery of hydrothermal circulation at the mid-ocean ridges and details of low temperature off-axis circulation. But what you can see in the diagram is the light color is the input flux of bicarbonate and the major elements in silica to the ocean, and the black is the output fluxes known at that time. Calcium was forced to be completely removed, and so that was balanced. But if you look at sodium, magnesium, silica, and potassium, and bicarbonate, the input fluxes were much larger than the output fluxes. And so in that paper, they hypothesized that a reverse weathering reaction within marine sediments is critical for removing the major elements sodium, magnesium, and potassium from the ocean and converting bicarbonate to CO2. Okay? After that, hydrothermal circulation was discovered, so that helped with the magnesium budget. It helped a little bit with the bicarbonate budget, but until, even today, we don't understand the sources and sinks completely of any of those. Okay? Okay, but that was the birth of this idea of reverse weathering, where you consume cations from seawater and authigenic clay minerals, and that has an impact on alkalinity and generation of CO2. And so this is examples of that, and so we've known about reverse weathering for some time. That was a hypothesized, and if you look at pore water profiles, you can see that there's uptake of potassium and magnesium along continental margins as well as in the abyssal environment in most everywhere, not everywhere, but in most everywhere. And so you can see a very sharp, this is depth, meters below seafloor. This is a Nicobar fan off of Sumatra, but decrease in potassium concentrations and a decrease in magnesium concentrations is a function of depth. So the solutes are diffusing from seawater into the sediment column and being precipitated in a mineral phase. For potassium and some of that magnesium, those mineral phases are authigenic clay minerals. And so this is widely observed, okay? And so you can use that to try to estimate global rates of reverse weathering. There's also been experimental evidence taking sediments from anoxic sediments into the lab and letting them react, and there's experimental evidence of reverse weathering as well. Right? And so the general reaction is that you take up silica, bicarbonate, and cations from solution, in this case pore water, as well as aluminum, and precipitate clay minerals. And in doing that, you convert bicarbonate to carbonic acid, and so you're consuming alkalinity through reverse weathering reactions. Okay? And that helps balance that alkalinity budget. All right, but it's not that simple in marine sediments, and so I'm going to now say that marine sediment weathering is really sediment alteration, and that there's both forward weathering and reverse weathering that occurs, and the balance between those two is what is important for alkalinity. Okay? So silicate minerals that enter the marine environment undergo dissolution because they're out of equilibrium. The environment in the ocean and in pore water is very different from the environment from which they form. Think of a plagioclase being formed from a volcanic system or something like that. It's out of equilibrium. And so as particles enter the ocean, they undergo dissolution and forward weathering processes. Okay? And so that's this reaction here. It's exactly the same as the Urey reaction, where silicates dissolve, you convert carbonic acid to bicarbonate, and have dissolved cations in solution. Those dissolved cations can then precipitate as a clay, and that's reverse weathering. So clay formation is reverse weathering. And so everything that's on the right-hand side of that equation is now on the left-hand side of the equation, and you convert bicarbonate to CO2. And it's really the balance between those two that matter in terms of total alkalinity of the ocean. Okay? And reverse weathering has to be tightly coupled to forward weathering because clay mineral precipitation requires aluminum, right? And that aluminum has to come from somewhere. In the ocean, the aluminum concentrations are low. So the aluminum required for authigenic clays is usually provided by the dissolution of those primary aluminosilicate minerals, plagioclase, amphiboles, clay minerals themselves, etc. Two recent papers, this is excellent, provide solubilities for 90 different silicate minerals, both in seawater and pore water environments. And so we now can do kinetic modeling of these processes a lot more robustly than we could in the past, and these just came out in the last couple of years. Okay? And so we're getting a much better understanding of silicates in seawater. All right, so as I said, these two reactions are coupled, and this is just a diagram in this recent Wellman et al. 23 paper showing that, where you can get aluminum from dissolving plagioclase feldspar. Clays are precipitating. You may take up some potassium and magnesium from clays. Biogenic opal is involved in the processes, And everything is coupled to POC degradation within these pore water systems. And so it can be quite complicated. All right. In the literature, authigenic clay formation is often described to reverse weathering, even though these minerals are also formed during marine silicate weathering. So it's really the balance between those two processes that matter. And the net effect of these two opposing reactions on seawater alkalinity and atmospheric CO2 is still uncertain because the global rates of those two reactions globally in marine sediments is poorly constrained. Okay. So now I want to step through some evidence of forward weathering. So we've got a lot of evidence for reverse weathering in marine sediments, and it wasn't until the last couple decades or so that we've had good evidence for forward weathering, and now we have a lot of it. Forward weathering is promoted by the degradation of organic carbon in marine sediments, and particularly in the methanogenic zone is very clear, but through fermentation reactions and other things. And so this is just the redox ladder in marine sediments. I don't want to dwell too much on it, but most of the anoxic pathways for degradation of organic matter produce alkalinity. Once you get through into the methanogenic zone in marine sediments, CO2 is produced rather than alkalinity. Okay, and so you're taking uncharged, let's say glucose in this case, and you produce an equimolar amount of methane and CO2 in the methanogenic zone. And that is a region where we see really high rates of forward weathering. So I want to talk about that. All right, so the pathways of methanogenesis and fermentation of methanogenesis are super complex, and there's a lot of them. But the two dominant pathways within marine sediments are CO2 reduction and acetate fermentation. And regardless of those two pathways, the net reaction is the same, where you take a mole of organic matter and you produce a mole of CO2 and a mole of methane. Okay, so for every methane mole you produce, you also produce a mole of CO2, and you produce ammonia through that reaction as well. And so because of that redox ladder, this is what we typically see in pore water profiles. It's super complicated. I don't want to get into it. I just want to highlight that when sulfate becomes depleted, then you get into this methanogenic zone where you're producing CO2 at the same rate as you're producing methane theoretically. Okay. Without sinks, due to the PO2 burial, the methane concentrations in pore water exceed 250 millimolar, and the concentration of CO2 theoretically should be 190 millimolar, up to 190 millimolar in the upper kilometer of marine sediments. As such, methane and CO2 in pore water are theoretically the third and fourth most abundant dissolved constituents, very different than the ocean. If you look at the ocean, methane concentrations are nanomolar, CO2 is around 20 micromolar. You get into the pore water environment, you have these through-the-roof concentrations of methane and CO2 because of microbial methanogenesis. So during methanogenesis, 6 times more DIC than alkalinity is produced. Okay, you're taking organic matter and you're producing CO2. The only alkalinity is coming from the ammonium. All right, so this is what we theoretically should observe within the methanogenic zone is DIC concentrations increase, and that's that CO2 produced by methanogenesis, but alkalinity should remain relatively constant. Okay, it's just the ammonium that's being produced. There are a lot of models for global rates of methane production, which then is equivalent to global rates of CO2 production in marine sediments, and you can see that the DIC concentrations are up around 200 millimolar once you get deeper in the sediment column. All right, so theoretically, alkalinity shouldn't be above around 50 or 60 millimolar once you get in the methanogenic zone. If you look at ODP drill sites in a lot of different locations, you see these alkalinity excesses. Alkalinity concentrations off Blake Ridge, which is on the US East Coast margin, are up at 100 millimolar. Concentrations of alkalinity off California are up at 120 millimolar. Even in piston cores in the Sea of Okhotsk, you're getting alkalinities up to 120 millimolar. That's not predicted. There's no reaction that I haven't talked about yet that would provide that. The CO2 should be that high, but not the alkalinity. Alkalinity should be constant within that zone. And so another thing I want to point out is that the concentration of primary silicates in all these cases in continental margins are actually quite high. Something like 20% of the particles are silicates. All right, we went out and measured DIC and alkalinity, which is rarely done in ODP, unfortunately. And what we observe in most settings is that the DIC and alkalinity concentrations are identical. Okay, so CO2 is being produced by methanogenesis. Alkalinity should remain constant, and so you should have an excess of DIC over alkalinity. Everywhere we measure this, DIC and alkalinity are equivalent. To do that, you need to have forward weathering occurring. Okay, and so you have CO2 being produced through methanogenesis. That CO2 is utilized for weathering primary silicate minerals, and you convert that CO2 to bicarbonate, and through that reaction, then you can have DIC and alkalinity be equivalent, and alkalinities are, up in 100 millimolar range. Okay, and so this is happening everywhere along continental margin environments. It's critical for a bunch of reasons, but one reason is that by buffering the system and generating all this excess alkalinity, you can drive authigenic carbonate precipitation and reduce that alkalinity reflux back to the ocean. And without it, you wouldn't have biogenic or authigenic carbonate preservation within continental margin sediments. It would be corrosive and all the carbonates would dissolve. So you actually need this to be occurring. So this is what we observe, and these are just simple models of what the pH would be in pore water and what the saturation state would be with respect to carbonate minerals given different primary silicates. But the take home is the green ones are no weathering, so you can see that the pH is down at 5.5. If you allow silicate weathering to occur, you buffer the system, and now you have more of a seawater type pH. Calcite saturation, in the case of no weathering, no silicate weathering in the methanogenic zone, you're highly undersaturated, and we're supersaturated when we have silicate weathering. So it's quite critical for the burial of carbonates in continental margin sediments. All right, so in a net sense, this is what we have is DIC and alkalinity are equivalent because of forward silicate weathering, and we drive down some of that excess alkalinity by the precipitation of calcium carbonates, but the global rates of that is unconstrained. All right, so all this set off a bunch of activity over the last 5 years in trying to better understand global rates of forward versus reverse weathering and what the real impacts are on total alkalinity. So I want to quickly step through this in 2 minutes on what others have learned, okay? And so the first thing is for major ions, this has no impact on alkalinity, but it's cation exchange. And I don't want to go through the details. The calculations are actually quite good, but this is sodium, potassium, magnesium, and calcium, and this is the percent of river flux driven by cation exchange as those riverine particles come into the ocean. Okay? So you have fresh water, and then you go into seawater, you drive exchange at the clay surfaces, and you can see they have a pretty large impact on major element budgets just in estuaries and when rivers dump into the ocean. The other thing that's been looked at in more detail now and much more seriously is just mineral dissolution, primary silicate mineral dissolution in seawater. And that's because of all this new solubility data. And so these are the mass loss rates that you would get for different minerals, assuming a residence time in seawater of a year. Even though there's some dissolution, more than 98% of the suspended riverine particles discharging the ocean are not dissolved in that year. Okay? And the last thing I want to show that has been done recently is trying to attempt to do kind of a global mass balance of the major elements in total alkalinity. These are benthic fluxes that are considering modeling results, measure pore water profiles, and shallow sediment samples from a variety of sources. And you can see that, well, anyway, that's that. And you can get an estimate of the total alkalinity flux just by charge balance and the cation release across the seafloor minus cation uptake. It can be used to estimate total alkalinity. I'm not going to go into the magnesium results. I'll just go finally into what the main results are. Is that when you take into account reverse weathering reactions and forward weathering reactions, these are the fluxes that you get for sodium, magnesium, potassium, and calcium. It drives pretty large fluxes, the net result in the major cations, but if you look at total alkalinity, it's a very small flux, okay? And that's because there's a slight more forward weathering than reverse weathering, but it's only 0.4 teramoles of alkalinity per year as a net if you look at only silicate weathering or silicate alteration. And that's not something that we would have predicted if we were just looking at forward weathering and certainly not reverse weathering, but when we look at them together, it indicates that silicate alteration in marine sediments may not have a significant impact on the alkalinity of the ocean, though it has an impact on the major element budget. That being said, that error or the uncertainty in that estimate is huge, right? 6 teramoles per year because it's done by charge balance with the other components. Okay. And so looking at this as kind of like an alkalinity budget of the ocean, this is what was known in 2020. We can now say, well, maybe the net is 0.4 teramoles per year. Anaerobic degradation of organic matter is a much more important source of alkalinity to the ocean. So it appears that marine silicate is important for the major ions, but it doesn't appear to be that significant for total alkalinity. But with the current uncertainties in the flux estimate of plus or minus 6 teramoles per year, it could be as important as anaerobic organic matter degradation, which is the largest marine source of alkalinity to the ocean. And so there's a bunch of things that we can do to improve this. These are kind of next steps that I would suggest. But the big thing is that the compilations, the data that's used for these extrapolations is pretty limited, particularly for surface sediments. Our extrapolations based on ODP cores are quite good, and there's a lot of undersampled regions. And so, we need to fine-tune those estimates a bit to get a better idea of what the alkalinity, what the source of alkalinity is for marine sediments, whether it is a source. But we're getting there, and it's awesome that so many people are actually working on this problem now. In the past, it was just a few. Now it's a lot more people. So I'm sorry that was fast, but those are kind of the main things. And again, a lot of people have contributed to this work. So thank you.
Okay, thanks, Evan. That was great. And we might actually hear more of that sort of thing in the afternoon when we talk about marine carbon dioxide removal. But for now, the coffee is ready, so we'll have a break for 15 minutes, and then we'll come back here for a panel discussion with the speakers and joined by two special guests.